Hi everyone, today we'll be going over our lesson on the greatest integer function. Before we get started, we'd like to introduce ourselves. My name is Audrey. With me are my partners are Joanne and Luna. Before we jump into the lesson, here's a quick overview of what we'll be learning today. We'll start with key vocabulary to understand the greatest integer function. Then we'll move into graphing and analyzing how this function looks visually. After that, we'll practice algebraic operation and simplifying. Finally, we'll apply everything we learned to an application problem. Floor function. First, we have the floor function, written as the floor of x. The floor function rounds a number down to the nearest whole number, even if the decimal is just really close to the next integer. For example, if x is 3.8, then floor of x is equal to 3. Because we dropped the decimal down and moved down, you can think of it like taking the number to the floor below it. Next is the ceiling function, written as ceiling of x. The ceiling function rounds the number up to the nearest whole number, no matter how small the decimal is. So if the x is 3.8, then the ceiling of x equals to 4, because we move up the integer. This is like going up to the ceiling above the number. The last vocabulary word is the fractional part, written as bracket x. The fractional part is only the decimal portion of a number after we move the whole number. We can find it by doing x minus x the floor of x. For example, if x is 3.8, the floor is 3, so 3.8 equals to 3.8 minus 3 equals to 0.8. So the fractional part just tells us the leftover decimal part of the number itself.
So now we are getting into graphing. Before we continue, let's talk about the parent function. All greatest integer functions have the same parent function, y equals the greatest integer of x. Here, we see a resemblance to stairs, hence why greatest integer functions are also known as step functions. We see how the function value jumps into the next integer value, and that's why we see open circles at the end of a step, because it does not include that y value and jumps to the next integer instead, and does include the y value, hence the closed circle. Let's look at another graph. As you see, the greatest integer function without transformations is the parent function. It is the same as a previous function. Now, some characteristics of this graph. The domain is all real numbers because although we see open circles, the next circle covering that certain value is closed, meaning it does include it. Range is all integers, not all real numbers. We don't have fractions, just whole numbers. X-intercept is an element of all x values in which x is greater than or equal to 0 and less than 1. Y-intercept is at the origin. Increasing intervals, the function is increasing at all x values. And behavior. As x approaches negative infinity, y equals negative infinity. As x approaches positive infinity, y equals positive infinity. Let's see a function with transformations and how it changes. Y equals 3 times the greatest integer of x minus 2. Here, negative 2 horizontally shifts the function 2 units to the right, and the 3 vertically stretches the function by a factor of 3. Some characteristics remain unchanged, like the domain, the increasing interval, and the end behaviors. But we do see a change in the range, the x, and the y-intercept values. If you notice, not all the output values are factors of 3. And because we don't have a special symbol for this, we must write the values individually on the range. The x-intercept is now x0, where x is an element of all x values in which x is greater than or equal to 2 and less than 3. The y-intercept is at 0, negative 6. Last graph. Y equals negative 1 over 2 times greatest integer of x plus 5. Again, the domain remains the same, but everything changes. The 1 over 2 horizontally shrinks our function by a factor of 1 over 2, and the negative reflects it across the x-axis. This makes our end behavior to reverse. As x approaches negative infinity, y equals positive infinity. And as x approaches positive infinity, our y equals negative infinity. This also reverses our increasing or decreasing interval. Now it is decreasing at all x values. Our x-intercept is again x0, where x is an element of all x values in which x is greater than or equal to 10 and less than 11. Lastly, our outputs are factors of 1 over 2. There is no special symbol for it, so we must write the values individually. Part 3. Algebraic operation and simplifying. Solving for greatest integer functions is simple. All you have to remember is to round x to the greatest integer less than or equal to x. Let's take a look at this equation. F of x equals 3 times greatest integer of x minus 1 over 2. We are looking at a only. F of negative 3 is 3 times greatest integer of negative 3 minus 1 over 2. We add these up and we have negative 3.5. So now one may assume that we are gonna be rounding to negative 3. But we must remember that negative 3 is actually greater than negative 3.5. So we will actually be rounding to 4. Once we have that number, we multiply by 3, then we get negative 12. Let's take a look at a second example. G of x equals negative 1 over 2 times greatest integer of x plus 5. We are going to be looking at b now. G of 0 equals negative 1 over 2 times greatest integer of x plus 5. Now, here, 0 is already an integer, so we don't have to do much change here. Negative 1 over 2 times 0 plus 5 is going to be 0 plus 5 is equal to 5. And this is also how you're going to look for your y-intercept. Last one, we have k of x equals greatest integer of 2x plus 1 minus 4. We are looking at C. K of a equals greatest integer of 2 times a plus 1 minus 4. Here we have the same procedure. 2 times a, 16, plus 1, 17. 17 is already an integer, so we don't have change. It equals to 17. 17 minus 14, 13. And that's how we get our results.
Next, let's look at a real-world problem. A warehouse company called Luna Stores charges for storage space based on complete cubic meters only. They ignore any fractional cubic meters when calculating the price. The storage cost function is C of V equals 30 plus 12 times the greatest integer less than or equal to V, where C of V is the monthly cost in dollars, D is the volume needed in cubic meters, and V must be greater than 0. The greatest integer less than or equal to V is the floor function. Now let's look at question A. Explain why a client needing 2.7 cubic meters of storage pays the same as a client needing 2.2 cubic meters using this function. Because the floor function is looking for the greatest integer smaller than or equal to the number, so for 2.7, we ignore the 0.7 and we got 2. And same for 2.2, we ignore the 0.2, so we got 2. All in all, for both clients, we are charged for only 2 complete cubic meters. So the cost is 30 plus 12 times 2 equals $54. Next, let's calculate the monthly storage cost for 0.6, 2.0, 2.7, and 4.3 cubic meters. To solve this problem, we need to use the function C of V equals 30 plus 12 times the greatest integer less than or equal to V. Now let's look at the first volume. The first volume is 0.6 cubic meters. The greatest integer less than or equal to 0.6 is 0. So C of 0.6 equals 30 plus 12 times 0 equals $30.
The second volume is 2.0 cubic meters. The floor function of 2.0 is 2, so C of 2.0 equals 30 plus 12 times 2 equals $54. The third volume is 2.7 cubic meters. The floor function of 2.7 is 2. So C of 2.7 equals 30 plus 12 times 2 equals $54. The last volume is 4.3. The greatest integer less than or equal to 4.3 is 4. So C of 4.3 equals 30 plus 12 times 4 equals $78. Now let's look at the last question. A client has a budget of $75 per month. What is the maximum volume of storage they can use without exceeding their budget? From the scenario, we learned that the client have a budget of $75 per month. So we got the inequality that C of V is smaller than or equal to 75. Because C of V equals 30 plus 12 times the greatest integer less than or equal to V. So 30 plus 12 times the floor function of V is smaller than or equal to 75. Then we substitute 30 on both sides of the inequality. We get 12 times the floor function of V is smaller than or equal to 45. Next, we distribute 12 on both sides of the inequality. We got the floor function of V is smaller than or equal to 3.75. Since the floor function of V must be an integer, so the greatest integer less than or equal to V must be smaller than or equal to 3. If the floor function of V equals to 3, then V can be any volume bigger than or equal to 3, but smaller than 4. Moreover, because the storage volume can be less or equal to 0, so the maximum volume is any number greater than 0 and lesser than 4.0 cubic meters. Next, let's verify our answer with two examples. The first example is when the volume is 3.9 cubic meters. The floor function of 3.9 is 3, and the cost is 30 plus 12 times 3 equals $66. Because 66 is less than 75, so it is under budget, and it's a correct one. When volume equals 4.0 cubic meters, the floor function of 4.0 equals 4, and the cost is 30 plus 12 times 4 equals $78. Because $78 is greater than $75, so it is over budget. These two examples help verify that the maximum volume is any number greater than 0 and lesser than 4.0 cubic meters. Here's all the link that we used. Thank you, everyone.